Draft physics video presentation. Yay. So I don't know what I'll title this or exactly what the point is, but I have in the past sort of pointed to this guy before, Michel van Biezen. He's a college professor, I think, somewhere or other, but he has these, online tutorials, whatever, on almost every physics subject imaginable. And yeah, a lot of math and stuff, but some of them are pretty good and blah blah blah. So I'm generally positive. So this is the beginning of a series on the electric field understood, and so I just thought it'd be an opportunity to contrast some points and just make the point that I think this is a place where physics just seems to me, this is a place where people could make kind of obvious arguments about a misunderstanding of electricity and magnetism, in the sense of thinking of these things as different phenomenon when they're just manifestations of the same thing. And it seems to me to be right almost in your face that the idea, the holy grail of magnetism is this idea of the monopole, the ability to separate a magnetic pole and to have one, just a north magnet or just a south magnet. And in my opinion, it's kind of obvious that what that would be is just a clump of protons or a clump of electrons. That if you could take a whole pile of electrons and put them in a clump, force them together through some mechanism, that you would have essentially the magnetic monopole, because the proton and electron are the origins of magnetism, and they're the mechanisms, especially the electron, of what's called charge. So in this sense, electrons and protons are the monopoles of the magnetism, and electricity is just forcing magnetism through a conductor. It's not electricity traveling through the conductor, it's magnetism, and the magnetism is pushing electrons, and that's really all it is. And so if somebody has evidence of some experiment or some reason to believe that isn't true, that somehow it can't be true that charge is just a manifestation of magnetism, and that there is such a thing as an electric field, when no, it's just a magnetic field. You can have a weak magnetic field or a strong magnetic field. The weak one they call EMF, and or EM something or other, E something or other, and and then there's this magnetism, the consequence of anytime you arrange anytime you do something to manipulate electrons and protons to segregate them in some way, which electricity moving through a wire essentially is, you'll create some level of magnetism, because it'll start filtering the field energy. Alright, and the other thing they don't do is when they talk about these forces, they never account for where the energy comes from. And so I just thought I would point some of that out. So I don't know, this might not be for everyone, but I'm going to do this video at least, and maybe I'll do some others depending on how interesting his videos are in terms of what statements are made. Something like that. So anyway, he's basically saying this is what is an electric field, and he's going to provide an understanding or an explanation, and I would argue the explanation is weak on cause. Good on effect, but weak on cause.
Electric field is a region of space affected by charge that's nearby. Now,
okay, so it's a region of space. So obviously I would argue that the space isn't changed. This isn't bent space or something. The space is filled with something. And it's filled, in the case of with charge, with lines of essentially magnetism. And that's how the space changes, is that there are places in the space that are now rays of something where they were just mixed before, when it was just gravity. So again, the whole idea of charge is that the little elements of charge, the electrons and the protons, are filters, and when those filters become at all segregated, that is, not mixed, then they produce some level of magnetism.
It doesn't yet tell you what it is, and what we're going to do is go through a series of descriptions that help us understand what an electric field is. But essentially, an electric field starts at a positive charge and ends at a negative charge. So the direction...
So this is where we get into this direction thing, which I would argue, I don't like the word arbitrary, but I'm thinking they're being incredibly arbitrary. And first, we don't even have the plus and minus signs in the right place, you know, in terms of which way things actually move. And so this description is technically wrong in the sense that we already know that you know, there's no more field moving one way than the other field. It's magnetism, that is, it's polarized, which means there's one kind of energy moving one way and one kind of energy moving the other way. So it's two kinds of force. That's what we get into my red and black argument. The force is being segregated. So now the area between the two plates is now filled with lines going in both directions of different color or polarization.
The direction of the field is always directed from the positive side, from positive charge to a negative charge. One way in which you can tell an electric field exists is by placing another small charge inside the electric field.
Right. Now, the small charge isn't going to be some neutral thing, because the neutral won't tell you anything. It can't be mixed, in other words. So there's only the two ways it can be. It can be segregated in the sense that it can be a red or a black, or it can be a mixture of red and black. But that's it. So there's no perfect third thing to use as a test instrument. And so there's either something that can't detect the field because it's charged both ways, or something that's biased in one direction or the other. And because of that bias, they assume that the system moves in one way. And the prejudice is just what charge you use decides which way the field appears to move. So again, it just seems kind of obvious that talking about direction of the field is inappropriate, in the sense that it completely depends on what kind of charge, positive or negative, you place in the field.
If you put a positive charge in the electric field, it will experience a force in the same direction as the electric field, from positive to negative.
So, in the same direction of the electric field. No, it's not the same direction. It's the direction of what a positive charge does in the circumstance. And a negative charge will do exactly the opposite. So there is no field that's deciding, in a sense. I mean, obviously it depends on what it's being exposed to, more negative or more positive. But it's just repulsion in a sense. It's which one is more repulsive to the individual charge. But there's no direction to the field itself. The field itself has elements moving in both directions. Wherever you create an imbalance of electrons somewhere, you'll probably have an imbalance of protons somewhere else. So the argument is you can't break that sort of symmetry. So you're going to be stuck with a more negative or more positive circumstance no matter how you create it. So it's always going to be a bias, but the field is always going to be moving whatever way that bias is. And it's not in one direction. I don't know how to say it. It's just not quite appropriate to say the field has a direction.
If you place a negative charge in the electric field, then that negative charge will feel a force in the opposite direction of the field, from negative to positive.
Again, in the opposite direction of the field. Now there's no, like I said, the word he's using, field, is just inappropriate, because obviously the field, nothing moves in the opposite direction of the field. It's moving in the direction of the field it's being exposed to, based on what its bias is as a charge. It's moving in the direction of the field. Both charges are moving in the direction of the field that's affecting them.
We can actually figure out the magnitude of that force. It is simply proportional to the size of the charge you place in the field and the magnitude of the field. In other words, you can calculate the electric field strength by measuring the force on a small charge you place in the field. Simply.
It's just a way of saying is you have two objects, like in even gravity arguments, and and you want to find out the total force, okay, then you take both, you know, and do your math combining them, because it adds up essentially. But it's not exactly the right way to think about it. The big thing is creating more charge, and the little thing produces a less charge that affects the bigger thing. But the two are affecting each other just like gravity. But clearly there's a proportion. The bigger the thing is in terms of how big a magnet it is, or how well polarized it is, how pure the magnet is, the strength of the magnet will dictate how powerful the force will be. Sort of duh.
We take the force divided by the charge, and you have the magnitude of the electric field. Also notice that the electric field is in the same direction as the force if a positive charge is placed in the field. Notice that we also represent an electric field
if a positive charge is in the field. So again, it's just this bias towards positive, when it's really, they're both two things that are different. I mean, they probably never should have been described as positive and negative, you know, because that has this bias built into it. They're both equal entities that have reverse properties. So there should be something opposite and equal, not something positive and negative. It's more like right and left. Maybe that's a way to say it. Right and left doesn't have an obvious bias, where positive and negative has an obvious bias.
By these lines that seem to emanate from these positive charges on top of this object right here. Or
right, the lines that seem to emanate. So again, for the people, this is the beginnings of Maxwell's equations, basically. And that's what I've been pointing out, that these lines don't have any wave character. They're they can be drawn as spheres, you know, of intensity. But the real point is that these lines essentially represent the density of the force at different locations. So the more separation between the lines, the more force. I mean, the less force. But it's again an arbitrary way of just illustrating the fact that the thing radiates the force like a light bulb would radiate light.
Or we can represent the electric field by these straight lines right here, emanating from positive charges and ending on negative charges, assuming that there's
and again, but the truth, I would argue, would be is that there's negative lines going exactly the opposite direction and positive lines going one way. So there's black force, so left force going one way, right force going the other way. There are two distinctly different forces based on the prejudice, the bias of the charge. That means the protons, one's proton heavy on the surface, one's electron heavy on the surface, and therefore they filter based on that prejudice. So it's not a strong magnetism, it's a weak magnetism, but it's a magnetism essentially. It's two poles of the magnet being bent to face each other, essentially.
A metal plate here that has additional positive charge and a metal plate that has additional negative charge. You can see that the electric field goes from the positive charges to the negative charges in that direction. So let's read.
So again, it doesn't really do that. It goes both directions depending on the charge. You put a positive charge in, the positive charge will move towards the negative. You put a negative charge in, the negative charge will move towards the positive. The field's going both ways.
Some of these descriptions to see if you can kind of...
It just matters on which way the rudder on the boat is turned, or however you want to say it, but the currents are going in both directions, and the boat decides which current it can take by changing its rudder or whatever, which one it hooks onto.
Understand what an electric field is. First of all, it says that it exerts a force on a charge placed in the field. So an electric field is a region in space such that when you put a charge in that space, it feels a force. A positive charge will feel a force in the same direction of the field. A negative charge will feel a force in the opposite direction of the field.
Right. So again, the rhetoric, I would argue, is that it has nothing to do with the space. The space isn't changed. What's changing is the fact that with just gravity, the field energy is mixed, and so what's happening is, instead of being mixed, the charged plates or wires or magnets will filter that field energy and create magnetism. Polarized, segregated elements of gravity. Segregated red, black, electron affecting, proton affecting. Proton force, electron force, maybe is the way to say it.
Next, we can read here that it can be detected by placing a charge in the field and observing the effect on the charge. So normally you wouldn't know that there's an electric field around you, but if you place a charge in the field and then you observe what happens to that charge, you can see it experiences a force or accelerate because of the force that it experiences.
It will just detect a bias. So if there's no bias, it doesn't move. If there's a bias, that is something proton heavy or electron heavy in the area, it will move commensurate to its positive or negative charge. It's black or redness. It's electronness or protonness.
You can see the effect, and that tells you there is an electric field there. Next, and maybe I'm in the way here, so let me move over this way. It says here the strength of the field is proportional to 1 over the distance squared from the source of the field. So the source of the field typically are charged.
So this is good. So this is the inverse square law, and he points out that this law breaks down when you bring charges close to each other. And he says he'll explain that later in a later video, but I mean it's just the idea that as you bring the light bulb closer, it has lots of points where the rays are coming off of the light bulb, and they're coming off like peacock feathers in both directions, so to speak. They're coming off in a spherical way, spreading. And all that spreading loses its meaning when the two things get close together, because you can't spread and miss when you're closer. When something's far away and it explodes, only a little tiny bit of the explosion can hit me. But if I'm very close to the explosion, or I jump on top of the explosion, then all of the explosion hits me. And that's the difference.
Charges. So positive charges are the source of electric field. The farther away you go from the source, the charges, the weaker the field gets, and not just linearly so, but 1 over r squared, meaning if you're twice as far away.
So when they say linear, they could say bilinear, in the sense that the lines would be this way and this way, which means a whole half of a sphere is the inverse square law, essentially.
From the source, the field strength is now only 1/4 as strong. Now there's some exceptions to that. Is when you have a field between what we call two plates that are very close together, but we'll go into more detail of that later.
So that's what I was talking about. The peacock feathers now don't matter, but you can't miss. No matter which feather shoots the ray can't avoid the other plate. So the inverse square law breaks down. Now this also would be a point to point out when he's saying this inverse square law. He said, it is a circumstance of some note that the inverse square law, that this works exactly like gravity, that it's functioning like gravity, that it's functioning like light radiating from a light bulb. It's functioning like the light you perceive with this hand is doing the inverse square law. 4 times smaller here than here. And you know, to me, more indication of why they should be unifying these forces, because they have too much in common. Too much in common to pretend one is caused by bent space and one is caused by virtual photons. Way too much in common to play this dichotomy of electric field, magnetic field, light field, neutrino field. I mean, it's one field.
We talk about capacitors and capacitor plates. Next, we can read here that the field can be represented by electric field lines. So these lines are called electric field lines. And what they do is, since the electric field is a vector quantity, it has both magnitude and direction. In other words, electric field has a direction because it always goes from positive to negative charges. Well, it doesn't go, but it's directed from positive to negative charges.
And so part of this is if you put two charges, the two monopoles together, you know, if you took a positive charge and a negative charge and did these lines, the point would be is that you could draw a continuous line around the both of them that would have equidistant lines, and those would give you the field lines that are often drawn that look like a topography map, and so that gives you those the classic magnetism lines going around the magnet would be based on just connecting lines that had equal distant number of intersections with the radiuses. But again, nothing in this basic description of electricity that has anything to do with waves.
And it also has a strength, so the field can be stronger as you get closer to the source and weaker as you go farther away from the source. Now, the electric field lines show you the strength by how dense the lines are. When the lines are close together, then the field is stronger. When the lines are farther apart, then the field is weaker. That's how those electric field lines are a good representation of the electric field in that respect. You can also call them arrows, and again, it indicates magnitude and direction of the field. The direction of the field is from...
So, in a sense, they illustrate, in just a simple two-dimensional way, the inverse square law, which is really the point, mostly. But, yeah, well, they illustrate half the effect, but it's proportional because it's half. So, to get the full effect, you'd have to kind of draw a cube. I mean, a four-sided rectangle, and get the size of the rectangle would be 4 times bigger as you got further away.
Positive charge and negative charge, just like we mentioned before. Whenever there is a field and there's a direction, let's say it goes from bottom to top, that means that on the bottom there's positive charge, and at the top there's negative charge. So that's always how we know the direction of the field. The strength of the field can be calculated. Now,
so again, this idea of positive and negative having these identities of difference, it's like I said, it would be better called left, right, or top, bottom might even be better, because that doesn't have the same bias. Like one is something and one is nothing.
We had one way here. We can place a test charge in the field and then measure the force on that test charge and then say that the electric field is simply the force divided by the charge you place in the field. But it can also be calculated like this.
I mean, another way to understand the bias is just to understand that if you move electrons off of protons, you can do that to varying degrees. So you can make something very, very weak in the number of electrons, or you can make it very strong in the number of electrons. But you could do the same thing with the protons. So, yeah, I don't know a better way to say that.
It is equal to 1 over 4 pi epsilon naught. Now, or epsilon sub naught, as I like to call it. Well, we'll talk about this in just a moment. Also, times the charge divided by the distance from the object or from the charge squared. So the stronger, the greater the charge, the stronger the electric field. So the more charge you place on here, the stronger the field becomes around there. And
so this is more now going to get into the bit about what if there's an atmosphere between the two charged plates. And, you know, so obviously it changes how well the force can move through the field and how much effect it's going to have. I mean, it creates the opportunity for the electrons to move through the atmosphere, essentially, to balance a charge. So they're able to move through the, that's the best way to say it. Yeah, there's probably some way to say it. I mean, I'm just saying, the more atoms you put in there, the more potential there is for electrons to be able to make the trip. But they can't make the whole long trip through empty space, because electrons can't fly straight. You know, they can't. Well, they can, but the force has to push them the whole time. What's a better way to say that? Yeah, we just go on.
It's proportional as 1 over the distance squared, as we mentioned before. The farther you go away, the weaker it gets. Twice as far away, 1/4. 3 times as far away, 1/9 the strength. But then we have this 1 over 4 pi epsilon sub naught. Sometimes this fraction, 1 over 4 pi epsilon sub naught, is also called K. K being 9 times 10 to the 9th newtons meter squared per coulomb squared. But we will talk about that in some later examples. Now, that epsilon sub naught has the value by itself of 8.85 times 10 to the minus 12 coulomb squared per newton meter squared. Now, what is...
Right, and then if you multiply it by 4 pi, then you get this other number of 9.9 something or other. Obviously, it just turns into a percentage. The 1 over thing just means we're going to make it a percentage of permutivity, you could argue. So how much of the field survives in terms of its strength. And so the closer, the bigger that number gets, the more the more energy you retain in terms of the field strength. And the smaller that number gets, the more you lose.
This epsilon sub naught. Well, this epsilon sub naught is called the permittivity of free space. 1 over that represents the opposition of space to forming an electric field. In other words, the greater epsilon sub naught is...
Okay, so it's not the opposition of space. It's the opposition of the matter in the space. So it depends on what atmosphere is in there. If it's full of water or it's this or that. Depending on what the atmosphere is, it will dictate. So it's not really about space. It's about mediums that it's traveling through.
The more difficult it is to form the electric field, the weaker the electric field becomes. The smaller epsilon sub naught is, the stronger the electric field becomes. And that is evident by realizing that epsilon sub naught is in the denominator. Make this bigger, this becomes smaller. Make this smaller, this becomes bigger. Space, free space out there,
I said it backwards, I think, but yes, you get the point.
Has the property that there's a certain amount of permittivity to form an electric field or opposition to form an electric field, depending upon how you want to look at it, either in fraction form or by itself. But what that means is that if you are in a different location where this is a different value, then you have a different strength electric field. So there seems to be some relationship between the properties of space and how strong an electric field can be formed by placing charge in that free space. By the way, when you're inside a dielectric...
The catch is, with dielectrics and the rest of it, is that the matter you have between the charges, okay, it's not free space, it's filled with matter. The matter can become also charged and therefore contribute to the field. And so in the sense, like you could say iron filings are doing that around a magnet. When they become magnetized, they're like little magnets and they line up and they become a line of magnetism. So yeah,
material, it turns out,
but they are not as nearly as they don't make as big a contribution as the original source. It's a weaker magnetism.
That the permittivity inside of dielectric is some constant times epsilon sub naught, which is of course the permittivity of free space. And since k is always greater than 1, if you're not in free space, this is therefore a bigger number, and therefore the electric field is weaker inside the dielectric material. And we'll see a little bit more about that as well. What's interesting is that the units of epsilon sub naught, the units of the permittivity in free space, is equal to F over m, F being farads and m being meters. And so a farad is a measure of capacitance. It's a unit that we use to measure the capacitance of a capacitor, and a capacitor is able to store charge. Let me get out of the way here. So it gives you an indication of how much...
Yeah, well, all the capacitor is really doing is creating a place for charge to be held. So it's creating a really big plate, in a little strip, and rolling the two plates next to each other really close with an insulator between them. Essentially, that's what the dielectric is an insulator. And so then you can create a big surface inside a little thing. So you're storing the charge not in the dielectric but on the plates. Some dielectrics will store charge like glass and stuff, but anyway, that's a whole nother subject.
Charge can be held by indicating the capacitance of a material. So free space in a way has a way to hold charge, causing an electric field to exist. So there's some relationship there between capacitance, the capacity to hold charge, and the capacity to set up an electric field.
Well, it's really about the ability to maintain the electrical field, the charge difference. So what you're trying to do is stop the electrons from flying across space and destroying the difference between the two surfaces. One side is electron heavy, one side is electron light. And the electrons, unlike protons, can more easily fly to the other side and neutralize the charge. So that's the point. You need something between the charges to prevent the electrons from flying from one side to the other.
Again, there's some property of space that allows us to do that, or not us, of course, but nature to do that in a certain way. And then here at the end, we can say that the larger the electric field, the larger the forces on charges. So ultimately, charges placed in space form an electric field, and the more charges you place, the greater the electric field strength, and the stronger the field, the more effect it has on other charges you place there.
So the argument, that argument is kind of deceptive, because if you mix all the charges, you'll end up with no net charge. So they have to be segregated charges to be strong in terms of their electrical effect. Just placing charges does not create electrical potential. You have to segregate the charges.
In other words, electric field allows charges to interact with one another, and that's basically the purpose of an electric field in space. Without an electric field, there wouldn't be any interaction between charged objects and between charges, and then nothing could exist, because it's ultimately the forces between charges that holds the atom.
So here he's pretty much getting to the point, is that the forces between charges, which is magnetism. Magnetism holds things together. We all understand how magnets do that, and how magnets keep things apart. And that's exactly the tension that's inside of every atom. The electrons hate each other, the protons hate each other. That's the protons are the strong nuclear force, in the sense that they're the force that's holding them, forcing them together, is the strong force. It's not really that strong, because it has to do with the fact of the leakage, as I've pointed out before, is that if you put an electron between two protons, the two protons can get much closer together, because all the force leaks out. There's no repulsion between them. You dissipate the repulsive force. So they think it's a strong force because they think when you put two protons next to each other, there's a huge amount of stuff trapped between them and creates a lot of pressure. But if something leaks the pressure out, then there's not that much force. So they think protons are too close to each other, but they're really not. But anyway, but clearly if you put them in free space, without the electron to seep the energy out, to provide the relief valve, then they will have a very strong repulsion, just as electrons will in the same circumstance. But anyway, so it's clear that they're behaving like magnets. The parallel is like so obvious, and yet they're calling it an electric force rather than a magnetic force. And so if anyone cares to make some sort of argument about what's stopping them from just jumping to the what I consider a reasonable conclusion, that electrons and protons are the source of magnetic function. It's exactly why magnets become magnetized, is because electrons and protons become imbalanced in their orientation. That's what a magnet is. That's what the domains of a magnet are. Is just too many electrons, two electron, what's the right word to say, exposure. The face is more electrons and the face is more protons, however you want to, the orientation of the electrons and the protons are what creates magnetism. Then they already have that idea, that notion, that it's how the atoms are stretched and that they become the magnetic moment. They become electron heavy or proton heavy at specific instances. Why can't they just take the leap and say, yes, it's a magnetic moment that creates electrical charge? And this whole idea of segregating electricity into a separate force, as if this force that's moving between two charged bodies is anything other than magnetism, when it does exactly what magnetism does. That is, you can create static charge and have a balloon stick to the wall, and it's not sticking because of some electric charge, it's sticking because it's the electric charge is creating a magnetic field, and the magnetic field is what's sticking the balloon to the wall. It's weak magnetism, but it's real.
Atoms together, and that causes atoms to form molecules and have that interaction in that respect. So a very necessary thing for matter to exist, and something that, of course, we're going to learn all about as we're learning more about electricity and magnetism. So
Right, so he's basically blaming electricity for holding atoms together when, why? Why the prohibition against the obvious connection between the magnetism is what is the controlling force in terms of repulsion and attraction. And attraction would be the absence of repulsion, by the way. So, okay. I think we did
Hopefully,
our job.
that gives you a better idea of what an electric field is.
So, like I said, he's been doing these videos for years. It's a huge reservoir of knowledge and stuff, and it doesn't get too many views, but it's really good stuff in my opinion. And I did attempt to get him to be interactive, but doesn't seem to have any interest in that. Didn't respond to my provocations and such. Jeez, such old videos. Some of these, this is like 10 years old or something. Anyway, YouTube's terrible. I mean, I just noticed how you can't search on channel pages anymore. At least I can't seem to find a way to do that. And when you search in the main thing for like a channel name and then a word, you get videos from all kinds of other channels. And so you can't search channels for specifically labeled videos, which that's a basic search function. I mean, it really, Google is so obviously anti-organization and functional search, and you can see it with their own website. They own YouTube, and nothing on YouTube is rationally searchable. And that should really give people an indication that maybe we shouldn't let Google control the fucking internet. I mean, damn. And something else is obvious again, just like, whoa. We're giving basically license to define the internet to a company that can't even create rational search mechanisms on their own website. And that's not even the truth. They had them and they destroyed them. They've systematically, over the 10 years, they have systematically broken every mechanism that allowed content on this website to be organized by the viewers, to give the user control over what he can find and see. They systematically broke every mechanism that gave the users the power. And the fact that this shit doesn't bug any of you bastards really pisses me off. You're not smart enough to figure out this is bad. Shit. Anyway. Yeah, I think that's enough. I could throw in some comments, but why bother? We'll save them for some other time, and such, and so forth and whatnot. Nothing brilliant. So, Okay, until next time, such.